In part 5 of module 6, we're going to be talking about isentropic efficiencies of steady flow devices. So we remember that we've already looked at some of the efficiencies in this class. So one of the efficiencies was, for example, the heat engine thermal efficiency, or also the coefficient of performance of our refrigerators or our heat pumps. So if you remember, the efficiency for our heat engine was equal to N thermal is equal to work net over QH. Now what we're going to try and do is we're going to try and find expressions in this part of the module. We're going to try and find expressions for efficiency of single flow steady state devices such as turbines and compressors. So we're going to find our efficiency for single flow steady state devices. And we're going to be looking at two devices in particular. We're going to look at turbines and compressors. Now, in your book, they also look at nozzles, but we're going to focus on turbines and compressors because we don't want to do too many of them. We want to understand the process very well for turbines and compressors. And if you understand those, you can also apply it to nozzles. Nozzles are a little bit different, but overall it's pretty much the same. But the idea here is to use this so that we can solve problems with turbines that are not necessarily perfect using our ideal process. Okay, so let's look at turbines first. So for turbines, we can say that the ideal process for a turbine is a reversible adiabatic process. And we know that if the turbine is adiabatic, we usually have an isentropic process. Okay, and the reason why we have an isentropic process is because there's no heat loss. And if it's reversible, it means that we're essentially not changing the entropy from our inlet to outlet, essentially. So usually in a turbine problem, you would be given the P of the inlet, the temperature of the inlet, and for example, the pressure of the exit. And these are the inlet and exit conditions. Now, in real life, a real turbine loses some heat. And a real turbine actually has an irreversible process. The process is irreversible. There are some losses within the system. And we know, essentially, if it's irreversible, we know that entropy increases. So we know that SE is greater than SI. The S coming in is greater than the S. The S coming out is greater than the S coming in. So we can say that entropy increases. And we can say that our efficiency for the turbine can be written as follows. So the efficiency of a turbine can be written as N turbine, so efficiency of turbine, so we'll write is equal to work that the turbine would do over the work isentropic. And that is the work over the work of shaft. And through a little bit of manipulation, you can actually write that this is equal to H in minus H at the exit over HI minus HE of the isentropic process. So this would be essentially your H in is going to be the same in both cases. Okay, what's coming in is the same in both cases. What's coming out differs by the fact that this is the real HE and this is an HE for isentropic. Okay, so that would be the main difference. And it's the same definition for a gas turbine, and we can actually draw a TS diagram of what we would have in terms of our inlet and exit. So let's look at what we would have in a TS diagram for turbine. So we would have a process that looks something like this. We would have on a TS diagram, we have our phase system, and usually the pressure and temperature of the inlet, we usually have some steam coming in. So we have a superheated vapor coming into our inlet. We can call this I. And what happens when we get to the exit, if we have an isentropic process, we actually have this go straight down into, and we'll call this ES, into our exit of our isentropic system. Okay, there's no change in entropy within our system, and our temperature goes down as we go through the turbine. Some of the temperature is essentially used to power the turbine, essentially. Okay, the heat is converted to work. Now, if we draw some lines for the processes, we would jump from a line of here where we have our constant temperature, and then our temperature would increase again as our S increases. Essentially, we can have our lines of constant pressure along the system, and the pressure at the entrance and the exit won't change. So this would be PI, our lines of constant pressure, and PE. So in a real process, since S changes, in a real process, what happens is we actually have a deviation from this ES, and our process actually deviates a little bit down to here. So our real exit would show on the TS diagram a little bit to the right. Okay, so we can see that our exit would shift a little bit to the right. Okay, so essentially what we're saying is that our S increases a little bit for the exit. And this will allow us to solve for a problem where we don't have necessarily a turbine that we know for example, we know that a turbine is not ideal. A turbine is not a reversible adiabatic process. We lose some heat. And if we can find ES, from ES, if we know the efficiency, we can find E. Or if we know E and ES, we can then, the points, we can then find our isentropic efficiency, essentially. Okay, so that's for turbines. Now, for compressors and pumps, we have the same type of system, except the system is reversed. So We also have an ideal reversible adiabatic. So the ideal process is also reversible adiabatic. And the process looks something like this on the TS diagram. So in a compressor and pump, we usually increase the pressure. So we have a low pressure that starts at PI and a high pressure line, P, and this usually happens in the superheated region. So we usually have it already in the superheated region. And we go from a point I to a point ES, which would have no change in entropy. Okay, so there would be no change of entropy if we have an isentropic system. And if we don't have an isentropic system, we have something like this that goes to E, where the entropy increases as well. Okay, so the entropy always increases. And the efficiency of a compressor is equal to Ws over W. So we now have our Ws is above our W. Okay, and it's just for the efficiency of the compressor. That's how it comes out to a decimal form. So we have, because the compressor is flipped, we have HI minus HES over HI minus HE. And typically for a compressor, we have efficiencies of compressor is usually around 0.7 to 0.9. Okay, so it's not usually that high. Okay, now we also have efficiency for nozzles, and for nozzles, we actually can come up with an efficiency that is, so nozzles will not be on the exam, but the efficiency for the nozzle, and we won't study nozzles more, but the efficiency for a nozzle would be related to its velocity at the exit divided by 2 over the velocity at the exit isentropic divided by 2, both squared. Okay, so we also have the nozzles can also be solved, and here the velocity would be taken into account, and not just the efficiency due to HI and HE. Now, for a compressor, the shaft work could also include our velocity and potential terms, but they're usually negligible, so we usually don't include them. So the Ws over W could equal HI minus HE plus the velocity plus the gravity, but we usually don't take them into account because they're usually pretty negligible in terms of their size. So what I wanted to do in this last part was to go through 2 examples in your book, because I believe that learning through examples in this chapter is the easiest way to learn. And you'll actually see that these problems are actually pretty simple to understand and pretty easy to derive. Okay, so we went through how we can get the isentropic efficiencies. So now let's look at how we can come up with some solutions to some examples. So I'm going to copy over an example from our handout. And this problem is an example problem in your book, so you can follow the example solution. Although the example solution might be a slightly different to mine, you can also follow it. So we have a question that says steam enters an adiabatic turbine steadily. at 3 megapascals and 400 degrees and leaves at 50 kilopascals and 100 degrees. So we have all the information of the turbine, and we're also told that the turbine is adiabatic. So we can draw a little bit of a little diagram to show what it would look like. If the power output of the turbine is 2 megawatts, determine the isentropic efficiency and the mass flow rate of the steam flowing through the turbine. So let's look at our system. So we have, let's say we're going to call this 0.1, okay, for the entrance. And we have our turbine. Okay, this is our turbine. And coming into our turbine, we have 3 megapascals at 400 degrees Celsius. And coming out of our turbine, we have 50 kilopascals at 100 degrees Celsius. And we can call this 0.2. And we also know that the turbine does some shaft work. Work dot is equal to 2 megawatts. Okay, or that's equal to 2,000 kilowatts. Okay, and we also are told that the turbine is adiabatic, so we know that Q dot is equal to 0. There's no heat loss in our turbine. And our goal is to find if we have an ideal process that is reversible or not, and how far we are from that. So we are asked to find the isentropic efficiency for the turbine. I'll just call it NT. Okay, and we know that to find, we're not given any information on velocity, and we know that our isentropic efficiency for the turbine is equal to the work over the work shaft. So it's equal to the work over the work of the shaft. And since we have no velocities and we can simplify our equation, we're always going to use this equation that says that essentially the work over the work through the shaft is just the work represented by what's happening in our system. So we have H1 minus H2A divided by H1 minus H2S. And we have to remember that this is a hypothetical. Okay, it is our best case scenario if we have a completely reversible system. It's a hypothetical scenario where we have our best possible situation. And so now what we're going to have to do is we're going to have to figure out our H1, H2A, and H2S in order to find our turbine efficiency. So how are we going to do this? Well, we know we already have state 1. So at state 1, we have that P1 is equal to 3 megapascals and T1 is equal to 400 degrees. Okay, or it's the T inlet if we want to. I call them 1 and 2 just to make it simple. And we know that this is equal to H. We need to find H1. So we can find H1 from tables. We have steam. Okay, we have steam in our problem, so we know that we have water. So we can go to our tables for steam. So if we know that we have 3 megapascals and 400 degrees, we can go to our steam tables. And we can go to table A4 or A5 actually. It's easier to read from A5 if we have pressure and temperature. So we go to table A5, we go to 3,000 megapascals, 3,000 kilopascals, sorry. And we see that Tsat is 233.85, so we know that we have a superheated vapor. So we go to table A6, and in tables A6, we're going to go to 3 megapascals, which is shown here on the middle bottom of the page right here. And we're going to go to 400 degrees Celsius. And we're going to be able to find our H1. So our H1 is going to be equal to 3231.7. So we can go back to our notes and write that we have 3231.7 kilojoules per kilogram. Okay, and we also have our state 2A. We're given our state 2A, our state actual for our turbine. We know that at state 2A we have pressure 2 is equal to 50 kilopascals and temperature 2 actual is equal to 100 degrees Celsius. Okay, so this is our actual temperature, so we're going to call it T2A. Okay, now from this temperature 2 actual, okay, we're going to call this actual, and this is what this value is here, right here. We're going to find H2A. Okay, so we modify our exit name from HE to HEA, which is our actual system. Okay, so H2A from state 2A, we have 50 kilopascals and we have 50 kilopascals and 100 degrees. So we can go back to our tables. So we can go back to table A5. In table A5, we can go to 50 kilopascals and figure out if we're inside the boundary or above. So we have 81.32 as temperature sat. So we're still in the superheated region. So we go to our superheated tables. We go to 50 kilopascals, which is our second box right here. Okay, so this is 50 kilopascals, and we can go to 100 degrees, and we get that this is equal to 2682.4. kilojoules per kilogram. Okay, now, how do we find H2S? The last value we have to find in order to find our isentropic efficiency is to find H2S. So actually the best way to do this is to actually look at a diagram. If we have our temperature versus S, we know that point 1 is at a pressure, so we can write the constant pressure line for, and let's say that point 1 is actually a little bit higher because we know it's superheated, so it's somewhere here. We have our point 1 is here, and this is a line at 3 megapascals. And we have another line here, which is at 50 kilopascals. And we know that point 2, our actual, okay, so we're going to call this 2A. Okay, our 2 actual is somewhere along this line. So we can say that our process from here to here is going to follow this type of line. So we have a TS diagram. Our temperature is going to drop from 400 to 100 degrees. And we know we're following our T2 actual. Now, our point 1, we have our value of temperature is equal to 400, we can write, and point 2, we have a temperature of 100. Now, how do we find 2S? Well, we know that if we have an isentropic process, we know that S1 is equal to S2S. We know there's no change in entropy. So our 2S value will be straight below our 1 value on this diagram. So essentially what we can say is that to find H2S, we can use the fact that the entropy does not change in this ideal hypothetical case. So we can say, if the process is isentropic, we can say that state 1 is still equal to state 1, it's still the same, okay? State 1 is just, we have P1 is equal to 3 megapascals, T1 is equal to 400 degrees Celsius, and in state 2, we are now going to have state 2S. And we know the pressure at state 2S is going to be the same. So the pressure always stays the same within the system, okay, regardless of if we have an isentropic system or not. Okay, we have to understand that the pressure at the entrance and the exit do not change. We're looking at the change between two different pressures. Now, the difference between 2S and 2A is that the entropy does not change. So we know that S1 is equal to S2S. And so from this, we can already find, we now don't know T2S. We don't know the temperature of 2S. Okay, so we can't solve this without, we can't solve this because we don't know what the temperature of 2S would be. So what we do is we find, if we can find S1, then we can use S1 as a property, which we know is S2S is equal to S1. And from S2S and P2S, we can find H2S essentially. That's how you would work through the problem. So to find S1, what we're going to do is we're going to go to our tables again. So if we go to our tables, we go to 3 megapascals for our first part of the process. We can see that right next to H1, we have the value for S1. It's 6.9235. So we know that S1 is equal to 6.9235. And that means that S2S is equal to 6.9235 because the entropy does not change. So from this, we can now find H2S. So H2S is wherever we have a pressure of 50 kilopascals and our S2 is equal to 6.9235. So going back to our tables, if we go to the 50 kilopascal in table A5, we can go to 50. So let me erase all the other annotations just so it's clear. So we have our 50 kilopascals, and we have to figure out if we're within our region of saturated vapor and saturated liquid, and we actually are. So we are in the middle of that region. So in order to find H2S, we need to find our quality. Okay, so we need to find the quality between 1.09 and 7.59. We have 6.9235, sorry. So we can find the quality from SF and SG, and the fact that we have S is equal to 6.9235. Once we find the quality, we can plug it back in with our H2, and we can find our H2S. Okay, so I'll let you do that in your own time, but H2S would be equal to 2,407.9 kilojoules per kilogram. Okay, so that means that showing you the process to find H2S, so we have, and I can tell you that the X going through the process would be equal to 0.897. Okay, so you have it as a value if you want to look for that specific number. And then just to find the efficiency of the turbine, we just plug in the values. So we have 3231.7 minus 2682.4 divided by 3231.7 minus 2407.9. And this would be equal to 0.667. Okay, or we can also call it equal to 66.7%. And so that would be our isentropic efficiency. So we're looking at the difference between our real process and an ideal process below, essentially. Okay? So part B, mass flow rate flowing through a turbine. So we need to find the mass flow rate. So for the mass flow rate, we're going to have to use the first law. So we're going to have to use first law adiabatic. And the first law adiabatic on the control volume is going to be equal to Q dot in minus work dot out is equal to mass flow rate times delta H plus delta KE plus delta PE. Okay, and we're going to cancel P and K because we have no information on those. And we're also going to cancel Q in because we know that there is no heat transfer in the system. And we also know that the mass flow rate in is equal to the mass flow rate out, which we're just going to call M dot because we have a single stream device. So we're left with minus work dot out is equal to M dot times H2A minus H1. Okay, and I'm using H2A because that's our actual system. Do not use H2S here, okay? It's our actual system that we're interested in. So we have minus 2000 is equal to M dot times 2682.4 minus 3231.7, and we have that M dot is equal to 3.64 kilograms per second, and that concludes our problem. So we can see it's a pretty simple problem to solve. We just have to find HI, HE, HI, and HS, and the HS is found, the H2S is found from the fact that the entropy in this, if the process is isentropic, this hypothetical situation, we can find H2S. And we also find out that this is in our sat mix region. So usually our isentropic process would be in the saturated mix region. Okay, so that's another thing to note, is that usually our isentropic process would land in process 2 in our saturated mix region. Okay, so let's look at another problem where we now look at a compressor, and instead of having water, we're actually going to use air. So we're going to do a problem with and this is example problem 715. The example problems are very useful in your textbook, and you can use the example problems as a basis, and then your study problems will help you solve some actual different problems as well, so you have those two things to help you out. Okay, so let's look at example 715. So in example 715, we say that air is compressed by an adiabatic compressor from 100 kilopascals and 12 degrees to a pressure of 800 kilopascals at a steady rate of 0.2 kilograms per second. If the isentropic compression of the compressor is 80%, determine the exit temperature of the air and the required power input into the compressor. So a little bit of a different problem where we're given our efficiency for our isentropic system, but we're not given any more information than that in terms of, so we kind of have to work in reverse compared to the first problem. So once again, I like drawing a diagram for these problems just to have. So we have a compressor, and coming into the compressor, remember our compressor is flipped. So we have 100 kilopascal air at 12 degrees Celsius. So it's the opposite of the turbine pretty much. And coming out of our compressor, we have 800 kilopascals. And that's all the information that we're given. We also know that the mass flow rate is equal to 0.2 kilograms per second. And we know our system has air. And we know that the work into the system is power in. Okay, so work dot into the system. Okay, so in a compressor, we're doing work to compress the air to a higher pressure, essentially. Okay, and we're also given that the isentropic efficiency, the N of a compressor slash pump, so we can use for a compressor or a pump, so we do C slash P usually, and in your formula sheet for the final exam, it's written as C slash P. We know that this is equal to 80%. Okay, and we're told to determine the exit temperature first. So A is the exit temperature. Now, when it asks for the exit temperature, we're actually looking for the temperature actual. Okay, so we want the actual temperature. We don't want the isentropic temperature of our hypothetical system. They could be the same, but in this case, we know they're not the same because the efficiency is not 100%. If the isentropic efficiency was 100%, then we know we have an isentropic system. In this case, we don't have that 80%. So we need to find T2 actual. And we're going to write a little 1 here and a little 2 here, just so we have our inlet and outlet as 1 and 2, okay, to make it easier. We also know that N for the compressor is equal to H2S minus H1 over H2A minus H1. Okay, just to make sure that we understand that that is the equation that we are working with. And if we draw a TS diagram of our system, just so that we understand our system in terms of the TS diagram, this is not mandatory to draw, but I like to draw it just to make sure that I understand what's happening. So we're usually in the superheated region here, especially with air. Air is usually not a liquid except at really, really low temperatures. So we know we're in the superheated region and we're compressing something. So we have a line of 100 kilopascals and another line above it of 800 kilopascals. And along this line, we have our point 1 is at the low pressure and is going to a point 2 actual, and our isentropic system would go straight up to a point 2S. Okay, so that's the difference between your actual and your S system. And you can see from this diagram, it's very clear that if I extend my y-axis a little bit, it's very clear that the temperatures are going to be different for A and S essentially. Okay, and we're looking for T2A. So let's write our states down and figure out how we can solve this problem. So we have a state 1, and at state 1 we have P1 is equal to 100 kilopascals and T1 is equal to 285 Kelvin. Then we have a state 2A, which is our actual result, where we have P2A is equal to 800 kilopascals. And we're looking for T2A. So we can't find T2A directly. That's the first thing we can write. And we can't find it directly because we don't have enough information. We don't have two descriptors we don't have two properties at state 2A. So we don't know the entropy, so we can't figure it out. So we can also write state 2s, which is our isentropic case where we have this, the isentropic case, which is a hypothetical case, where P2s is going to be equal to P2a. It's the same pressure. Okay, they always operate between two of the same pressures. And we know that S2s is equal to S1. And we also know that from this, we're hopefully going to be able to find our T2s. And we can assume that air is an ideal gas. And if we assume that air is an ideal gas, we can use our isentropic relations for ideal gas. So we can use our isentropic relations and these isentropic relations can be used for this process right here. So from the pressure, we can actually find T2s. So if we know we have an isentropic system, we can say that T2s over T1 is equal to P2s over P1 to the power of K minus 1 over K. So what is K? Well, K can be found from table A2. If we go to table A2 for air, we find that K is equal to 1.4. Okay, so if we go to table A2 for air, we have that K is equal to 1.4. We can see it here. Okay, and we just use the general value for K. We don't need to interpolate or anything. They also have K here at various temperatures, so you can be a little more precise and use it at an average temperature. So you could go through this and look at for an average temperature, but the value doesn't change that much, so you can just use the K of 1.4 in that first table, at 300 Kelvin, pretty much. Okay, it's not necessary to go through finding K at another value, but you can find a little bit of a better version. Okay, so we can now find, so we have K is equal to 1.4, so you can now find that from all our information, we can plug in all our information, and we can find that T2s is equal to 516.2 Kelvin. Okay, so plugging in all our values, we have P2s, we have P1, we have K, and we have T1, and by rearranging, we find that T2s is equal to 516.2. Okay, so now we have T2s, we have T1, and what we're left with finding is T2a. So how do we find T2a? Well, T2a is actually pretty difficult to find, right? We don't really know how to find it. So we're actually going to be able to find it using our efficiency equation. So our efficiency for the compressor, we remember, is equal to H2s minus H1 over H2a minus H1. And because we have an ideal gas, we can, and we don't have tables necessarily. I mean, we do have tables for air, so there's two ways to solve this problem. Okay, and I'm going to show you the two different ways. So one way, which is the preferred version, is to solve it with this problem here. So this is preferred. Okay, so we prefer solving it with this equation directly. Now, for any other gas, you can't really use this because you can't find H2A from your equation. So you have to rewrite this as CP average times T2S minus T1 over CP average times T2A minus T1. And the CP average between the two temperatures is usually going to be pretty much the same. It's not going to be exactly the same, but usually we're going to be able to cancel them because we're going to have very close temperatures between our actual and our isentropic. So we can say that this is equal to T2S minus T1 over T2A minus T1. This is called, we can call this the shortcut method. Okay, the shortcut version essentially just says that the efficiency of a compressor is equal to the change in temperature for isentropic over the change in temperature for our non-isentropic system. So we have T2S, T1, we have the efficiency of the turbine, so we can find T2A directly. Okay, we can find T2A directly between this relation. Okay, that's the shortcut method. Now, the preferred method is to use the actual H's for our values instead of just using our temperatures. For air, we have tables in table A17. So we can use table A17 and we know our temperatures. So we know T so we know temperatures at 1 and at 2S. So if we find the temperatures at 1 at 2S, we can find H2A. And then from H2A, we can find T2A from table A17. So let's look at how this works. So let's find H2S and H1 from table A17. So if we go to table A17, we know that T2S is 516.2 Kelvin. So we go to table A17, and we know that T2S is 516.2. So it's going to be between 510 sorry about that. It's going to be between 510 and 520. And we can see that H is the first value in this table. So we know that H is going to be between these two values. We can interpolate. And by interpolating, we find that H2S is between 513 and 523. So it's actually equal to 517.05 kilojoules per kilogram. Now to find H1, we use temperature 1. For temperature 1, we have a value of 285, and our H1 is actually equal to 285.14 kilojoules per kilogram. We actually notice that our H for air is actually very close to our temperature too. So it's an interesting thing to note. And now that we have H1 and H2S, we can say that the efficiency of our compressor, which is equal to 0.8, is equal to 517.04. Again, this is our preferred method, over 285.14, minus 285.14 over H2A minus 285.14. And so we get that H2A is equal to 575.03. And now, from this, we can go back to table A17 and find our temperature 2A matching with our H2A. So we go back to table A17, we look for where H is equal to 575.03, So it's going to be very close to this value right here. Okay, we see that we're at 575.59, so it's going to be very close to 570. And we find out from interpolation once again that T2A is equal to 569.5 Kelvin. Okay, so recapping this, we have an equation that says that the efficiency of the compressor is equal to an equation in terms of H's. If we want to take a shortcut, or we don't have air and we have another substance, or we don't have water or R134A where we have tables, but we actually have like nitrogen or something, then we have to use our shortcut. Now, in the case where we have air, we want to be able to use the preferred method, because the preferred method will yield slightly better results. We're not assuming that the CP is the same at the top and bottom, which is something that we have to do in the shortcut method. Okay, so it makes it a little bit longer, but using table A17 and interpolating, we can actually get better results. So we want to try and use the preferred method if possible when tables are available. If you have nitrogen or argon or any other ideal gas, you would use a shortcut method to solve for your problem, and you would get a pretty accurate result anyways. Okay, so moving to part B. So in part B of the problem, we're asked to, just going back to the problem, the required power input to the compressor. So we don't know the power input. So what are we going to do? We're going to use the first law again. And the first law is again Q dot in minus work dot out is equal to delta H plus delta KE plus delta PE. And we're going to get rid of KE and PE because we don't have any terms. And we're also going to get rid of our Q dot in because we have an adiabatic system. Okay, in the question we're told that the system is adiabatic. So we have minus work dot out is equal to m dot times H2 actual minus H1. Remember that when we're looking for a system, we're always looking for the actual number. And so we can write that we're going to find work dot out, and then we'll just convert it to work input at the end. Okay, I prefer finding the power out and then converting it to the input after, which would just be the opposite of power out. The other way you can do this is you can say that this term right here is equal to work dot in and solve for work dot in, but I prefer solving for work dot out first and then converting to work dot in at the very end. So we have that, then we can change this to work dot out is equal to negative m dot H2A minus H1. So if we didn't have the H's, we could use CP delta T. But since we have the H's, we can say this is equal to minus 0.2 times 575.03 minus 285.14. And we have that the power out is unsurprisingly negative. Makes sense. We have minus 58 kilowatts. So that means that the power input is equal to the positive of that. So 58 kilowatts. Okay, so work input is always the opposite of work out. Okay, so we end up with a power, work dot, remember, is power, is equal to 58 kilowatts. And that concludes our Module 6 lecture, as well as all the lectures with new material on this whole course. We will be doing a review for the final exam that is separate from this, with some information on the final exam. So stay tuned for that. It'll be posted later on in the semester.